Okay, so this is chapter 2 out of Faber, and this is the X-ray beam, how it's produced. So here's your objectives. Make sure you're able to answer the objectives that are listed here. X-ray production. How do we produce X-rays? So the production of X-rays requires a rapidly moving stream of electrons to suddenly be stopped or decelerated. So the negative electrode, which is called the cathode, is heated, and the electrons are boiled off. We call that thermionic emissions. The electrons are attracted to the anode, which we'll go into in another class as to how they're attracted. So the electrons are attracted to the anode, move rapidly towards the positive electrode, and are stopped or decelerated when they hit the anode. So X-rays are produced within the X-ray tube housing. So the X-ray tube housing is usually metal or glass, and you can see the housing all the way around here. We have the negatively charged electrode, which is here, which is our cathode end of the tube, and you can see that it is negative. And you can see here we have the filament within the focusing cup. There's a port or a window within the glass or metal housing, and we use that as part of our inherent filtration. There's also the positively charged electrode, which is the rotor, and it has the stator, which is an induction motor. So it uses magnets to spin the anode. This is the anode here. This is the anode stem, and the anode is made up of tungsten and rhenium on the disc, and we use the two different metals to help with the heat dissipation and the expanding and contracting of that anode. So the cathode, looking at it up close, it's the source of electrons. It has a filament current which produces your thermionic emissions, and it gives us an electron cloud. So when you're on the operating console and you see small and large focal spot, this is what we're talking about here. So we have the tungsten wire, and we use tungsten because of its high melting point. So we have this small focal spot, we have the large focal spot, and the focusing cup all the way around. And we use the focusing cup to kind of keep the electrons within one contained area. And it's for the space charge effect. The anode, it rotates to help dissipate heat. So it requires a stator and a rotor for it to rotate. And like I said, the stator's on the outside of the envelope, and it uses an induction motor with magnets to spin the anode. The metal that we use on the anode is tungsten, and we use that because of its high melting point and sufficiency in X-ray production. And we'll get into that further down the road. The target is what we use to decelerate or stop the electrons from flowing. The energy is converted to heat. Remember, it's 99.9% heat and less than 1% X-rays. So within the tube, we have bremsstrahlung and characteristic interactions. So bremsstrahlung interactions, it's called breaking or slowing down of the radiation. So it's 85% of the beam. Characteristic interactions, a projectile electron energy is at least 69.5 keV. When we're talking about kVp, that's kilovolts peak. When we talk about keV, we're talking about the electron energy within the tube. So keV, kilo electron volt. When we have at least 69.5 keV, the inner shell electron is energized, is ionized. And this is considered 15% of the X-ray beam above 69.5 is made up of characteristic interactions. So as you can see here with bremsstrahlung, you have your incident electron coming through, and it makes a turn. Anytime there is a change in direction, we consider that a scattered photon. So it's interacted with something and is making a turn. If it has just a real slight turn, it's going to give off a lower energy bremsstrahlung X-ray photon. Where this one, you can see it's coming in and it's making a really sharp turn, so it has a higher energy bremsstrahlung photon coming off. So with characteristic, what happens is an incident photon comes in and interacts with the inner shell electron. So this is your K shell, L shell, so it keeps going K, L, M, N, O all the way out. So what happens is it knocks this K shell electron out. So then the atom is very unstable. So it's going to take the L shell and drop it down into the K, and each one of these photons is given off every time it drops down a level. When the electron drops down to a shell that is closer to the nucleus, it gives off the photon called a characteristic X-ray photon. And this whole process is called characteristic cascade. So it's cascading down, 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 and giving off photons in return. So how does this work? So prepping the tube for exposure. When the rotor or prep button is activated, this is what we're talking about. This is everything that's going to happen. So on the cathode side of the X-ray tube, the filament current heats up the filament. The heat boils electrons off the filament, which is called thermionic emissions. The electrons gather in a cloud around the filament called space charge. The negatively charged focusing cups keep the electrons cloud together. The number of electrons in the space charge is limited, so it's called the space charge effect. There can only be so many electrons in that small little area. Once you get to that level where you can't have any more boiling off, you've hit your space charge effect. So on the anode side of the tube, when the rotor button is prepped, the rotating anode begins to turn rapidly, quickly reaching top speed. So, make an exposure. So after the activation of the rotor and the exposure is initiated. So, you pushed all the way down on the exposure button. On the cathode side of the X-ray tube, the highly negatively charged high negative charge strongly repels electrons. So that's interesting how they wrote that. So these electron streams stream away from the cathode towards the anode. So that's called the tube current. So what happens is here they've got the electrons boiled off. They're within the focusing cup. And so you push the button all the way down. They're pushed and pulled. So both towards the anode to the focusing track. So on the anode side, the highly positive charge strongly attracts the electrons in the tube current. These electrons strike the anode. X-rays and heat are produced. So when we're looking here at the X-ray emission spectrum, so the range and intensity of X-rays emitted change with different exposure techniques set on the control panel. So when we're looking, here is your number of X-rays and here is your energy in keV. So when we have 69.5, you're going to see this little characteristic tick in your graph. So you have Bremsstrahlung X-rays here, and they stop at 69.5 and higher. They switch over to characteristic. Characteristic cannot exist below 69.5. So that's what we're looking at here. So if you dial up, looks like 90 keV or kVp on your console, this is what your energy spectrum, your X-ray spectrum is going to look like. You are only getting a couple photons at your 90 kVp. You're mainly hitting around, 30 for your peak. So you have a few X-rays here in your characteristic range. All right, so when we're talking about quantity and quality, quantity is the number of photons in the primary beam. Quality is the penetrating power of the beam. Your primary exposure factors are kilovolts, kilovoltage, milliamperage, and exposure time. So when we talk about kilovoltage, it creates a potential difference. So it determines the speed of the electrons in the tube current. So higher the electron speed results in higher quantity of energy of the primary beam. Increasing the electron speed will increase the beam penetrability. So when you set your kVp to 72, you can see your X-ray spectrum here. If you set, 72. So if you set it at 82, you can see you have a higher power, a higher energy X-ray beam. So what's this tick? Yep, characteristic. Milliamperage, so the unit to measure tube current or the number of electrons flowing per unit of time. So MA is directly proportional to the quantity of X-rays produced. So you double the MA, you double the number of photons produced. So here you can see we've got our tick there, 69.5. We have 200 MA, we have 400 MA, directly proportional. You double the number, you double the amount that you're going to be producing. So exposure time. Exposure time determines the length of the time the X-rays are produced. Increase in time will increase the total number of X-rays produced. Exposure time and X-ray quantity are directly proportional. So here's some examples. So milliamperage times time is your MAS. So changing the MA or the time will change the quantity of the X-rays produced. Line focus principle. Okay, so this is a concept. This is something that we will go further into later on, but I want you to be introduced to it. So line focus principle is a relationship between the actual and effective focal spot. So the actual focus spot is the area on the anode target exposed to the current of electrons. So this right here is electrons coming in to hit the target. So this is your target right here. We have a 15-degree angle. So electrons come in. This is your actual focal spot size. Now, since it's at an angle, the effective focal spot size coming off is going to be smaller. So the effective focal spot size is measured directly under the anode target. So it's right underneath it. The smaller the anode angle, the smaller the effective focal spot. So as this gets smaller, as it goes from 15, let's say, to 5% or 5 degrees, this will be narrower. This will be smaller. If the angle goes to 30, so these electrons have more area to hit, so it's going to be bigger coming off. All right, the anode hill effect. I think we've talked about this before. So you have your anode, you have your cathode, your electrons are hitting your focal track and they're coming off. Now, they come off at an angle and they're coming off with a varying degree of intensity. So X-rays are more intense on the cathode side of the X-ray tube. So this is the cathode side over here. So you can see I have 120 for the intensity compared to 75 over here. So the intensity of the X-rays decrease towards the anode. So what you want to do is you want to place the thicker portion of the body part toward the cathode side. So one way to remember is fat cat. So cat for cathode and fat. So think of the thicker side towards the cathode side. Filtration. So we use aluminum. We add it to the X-ray beam to absorb low energy photons. So looking here, we have the total filtration is the inherent plus the added. And why we do this is to reduce the patient's exposure. So it'll reduce skin dose. So here within the X-ray tube, you have the collimator. We're going to blow it up. And you can see here we have, where are we? We have the oil. That's going to absorb some of the lower energy. We have an aluminum filter. And we have a mirror. Altogether, the filtration is used to reduce patient dose. Compensating filters. So we can use additional filters as needed for patients. So I just want you to know the basic concepts of it. So adding to primary beam to alter its intensity. So a wedge filter, and there's a trough filter. So for a wedge filter, as you can see, you put the thickest part over the thinnest subject part, that's the subject positioning. So here the thinner part's going to the thicker. So here with the trough filter, the mediastinum is pretty dense, so the lungs are not. So we'd use a trough filter, this is called trough filter, so that we could see the lungs and the mediastinum properly exposed. All right, heat units. Why do we have to worry about heat? So during X-ray production, most of the electron kinetic energy is converted to heat and can damage the X-ray tube. So how do we figure out what the heat units are? Most of us are using high frequency generators. I can't imagine anyone using less than a high frequency generator. I suppose they could be out there still, but your equation is going to be 1.40. So what you're going to do to calculate your heat units, you're going to take your MA times your time, or your MAS, multiply it by your kVp, and multiply it by your generator factor, which is 1.40. and that'll give you your heat units. And then there's graphs that you can check to make sure that you're not going to damage your tube when you're making exposures. So to extend the X-ray tube life, you'll want to warm up the tube. If it's been sitting and it's a cold tube and you get a patient and you're doing a lot of X-rays, really high energy X-rays, you could actually crack your tube. You can crack your anode. There's all bad things that can happen. So you'll want to warm up your tube if it's been sitting for a long period of time. You want to avoid excessive heat generations, and don't hold down the rotor button without making exposure. So a lot of your techs are saying, okay, rotor and then expose. You're not supposed to do that, and they're all going to argue with you, but do know that you are supposed to hit it all the way down, and once the anode gets to speed, it'll make the exposure, and that's going to take and extend the life of the tube. You want to use a lower MA and longer exposure times. Also, don't move the tube while it's energized. I don't know why you would ever do that, but don't ever do that. You also want to listen for any kind of unusual noises and report it so that it gets fixed before it blows up. So that is your basics, very, very basic in X-ray production.